just the remaining video, we're going to take a look at a couple of additional examples. And again, just the whole purpose of this series is just to kind of get you thinking about problem solving and thinking about modeling with different functions, and not me telling you directly what kind of function it is, but to kind of use context clues, thinking about the situation, what kind of model would be most appropriate. Well, we kind of know when we run into money what types of things we're doing, but suppose this is actually in March 2007, Third Federal Savings and Loan offered a 5-year CD. Now, CD stands for Certificate of Deposit, and you don't really need to know the specifics behind that other than what it is you make an agreement with the bank that you'll put in a certain sum of money and you'll leave it in there for 5 years, and they're going to pay you 5.15% nominal interest rate. Nominal interest rate is another way to say APR, annual percentage rate. So it really just means that's what they're paying you annually, but they're compounding it quarterly. So remember what that means. That means that they're going to pay this. This is the 1 year amount, but they're going to split that up into 4 quarters. Into quarters, really. At the same time, Chase Bank offered a 5-year CD at a 3.68 nominal interest rate compounded daily. Given that you want the future value of the CD to be $5,000 in 5 years, determine which account would require you to invest the least amount. Okay, so we know that in this case we're dealing with, we're not dealing with continuous compounding. It specifically says how often interest is paid, and so our continuous or our compounding formula is this guy here. And remember, this is just a basic exponential function. It looks really fancy. We've got the 1 plus because we want this to be a growth factor, and it's r over n because we're going to take the rate they pay us. In the first case, 0.0515. Remember, that's 5.15 over 100, and that comes out to this number. But it's going to be divided into 4 equal pieces because they pay this amount, but they pay it over 4 quarters. So in the case of Third Federal Savings, we're asking the question, we want to have a future value of 5,000. So that means that A, the output should be 5,000. We want 5 years. Well, that's the value of time, 5 years. N is the number of times interest is paid on a yearly basis, and in this case, it's compounded quarterly, so it means interest will be paid 4 times. So over the course of 5 years, at 4 times a year, we're going to pay the quarterly interest a total of 20 times. And we're asking what should the deposit amount be, which would require us to invest the least. Okay, well, at a rate of, oops, we forgot r is equal to 0.0515, we could do the math here. We could figure out 5,000 needs to equal some number times 1 plus 0.0515 divided by 4, raised to the n times t power. So 4 times 5 is 20. And so basically, this is going to be the quarterly rate that's paid, and it's going to be paid for 20 quarters. So we're multiplying the present value by that amount 20 times. Now, I'm going to plug this part into the calculator just so I can simplify. Whoops, I'm trying to get to the right screen here. And this could be solved graphically, but realistically, it's going to take us a lot more effort to solve graphically than it is to just simplify this down. Well, what is this? Let's think about the way this problem is written out. Now, you may not know what this amounts to off the top of your head, but what's here in the pink box, that's a single number, right? So let's figure out what that number is. 1 plus 0.0515 divided by 4 raised to the 20th power gives me a value of about 1.2916. I'm just going to round that, 1.2916. And that's p times that amount, right? Which is the same thing as 1.2916 times p, and that has to equal 5,000. Well, the reason I said solving graphically is probably harder in this case is because this is a simple linear function now that this has reduced down to a number, right? It's kind of like the form m times x plus 0. And so now all I need to really do is just divide. If some 1.2916 times something equals 5,000, then 5,000 divided by 1.2916 tells us what that factor should be. So divide 1.2916, and 5,000 divided by 1.2916 will give me 3871. So about $3,871.17 is what I would need to invest in Third Federal Savings in order to accumulate $5,000 at the end of that term. Well, I want to compare that out. The question is, which account would require you to invest the least amount? Okay, well, in this case, the interest rates are really quite different, right? The only difference is that this guy is compounded daily, so it's paying interest more often. What do we know about more compoundings? It generally amounts to a little bit more interest. Now, I think these interest rates are different enough to where you could probably say that this one's the better one to go, but let's just be sure, because sometimes our intuition is a little deceiving. So for Chase, I'm going to do this back in the black color, and we know that this is still, well, not still, I should say, this interest rate is at 3.68%, so 0.0368, or you could do 3.68% and find out that it's 0.0368, still for 5 years, and this is compounded daily, so we assume daily there's 365 days roughly in a year, and we still want to accumulate $5,000, but we want to figure out what should we invest today. So setup is very much the same, except that we just have to change the numbers over here. 1 plus 0.0368, but it's divided by 365. And the exponent is 365 times 5. That's the total number of times interest will be paid. So I'm just going to put that up there and put that in parentheses, because when we put in our calculator, again, it's going to be this right here is a single number. And I'm going to type in 1 plus 0.0368 divided by 365 raised to the 365 times 5 power, and that's going to come out to 5,000 equals 1.2020p. Okay, well at this point we should be able to confirm without doing the extra math that this is going to require a larger initial investment. Why is that? Well, because back here, look at the size of this multiplier. This was 1.2916. So if I multiply two numbers together and one of them is quote-unquote big, then the other really only needs to be small to produce 5,000. But if I take a smaller multiplier, then this number needs to be bigger bigger than it was before in order to still make 5,000. So 5,000, let's just verify what that amount actually is, 1.2020. This one would require an initial deposit of $4,159.73. Well, now you have to think about, okay, well, are there risks involved? Do I just rather invest more today? I mean, it's not that much more. Maybe I could afford to put that money away, and maybe I know that going with a certain bank will be more beneficial. So at least at this point, you have quantitative information to make that decision. And so we are dealing with exponential functions here. I think we pointed that out at the beginning of the problem, but exponential is any time we're multiplying a present value, and then we're multiplying that value, and then multiplying that value, which is exactly what's happening here. We're taking in this case, this is the daily growth factor, and we're growing the present value by 5 years worth of that daily factor, which is 5 times 365. In this last challenging problem we'll look at, we're looking at some data that the NSA, the National Security Administration, collects in order to be able to kind of make some predictions about the population. So the NSA often conducts studies to determine potential threats in the exchange of information. Suppose the NSA is interested in gaining an understanding of internet usage in a particular region of the country. They build a function, okay, to determine the number of hours a person uses the internet each week as a function of their age beyond 13 years of age. So now we're looking at, so let's just say that this is the person's age, and the output is the number of hours. And so we'll define this. We'll say A is age after 13. So for example, 0 would represent 13, and I'll just say 13 is equivalent to 0 in this representation here, and this is the number of hours per week. Hours each week. And so what we can gain from that now is we know what we're going to be comparing. So we're given some information. We're told that they find that a 13-year-old uses the internet for an average of 40 hours a week. So what do we know so far? Well, we know that a 13-year-old, someone who corresponds to A equals 0, uses the internet for about 40 hours a week. So we have a vertical intercept, in other words. And we'll come back to, actually, let's go ahead and plot that now. So because we're given data in this type of fashion, as opposed to given data in a table or given data in some other representation, because it's just a lot of written information here, it's important for us to represent that information as clearly as we can. So here's 10, 20, 30, 40. So a person who is 13 uses the internet for 40 hours. And so then they tell us they also find that an increase in age from 13 years to 14 years results in an increase in weekly usage by 2 hours. Okay, so if this person increases in age from 13 to 14 years of age, so from A equals 0 to A equals 1, the usage increases by 2. So over 1 up 2. So it kind of looks like that. And I'm not going to connect them because if I do, I don't want to imply that this is necessarily a straight line. The rate at which the weekly increase-decrease changes by is unknown. Okay, so the rate at which the weekly increase-decrease, so the increase from 0 A equals 0 to A equals 1 was 2, but this is arguing that the increase is not the same. And not only that, but it's implying that the rate at which the weekly increase-decrease changes by is unknown. Okay, so the best that we can do, and maybe this should have been a little bit more explicit, but we'll also assume that the rate at which the slopes change is constant. So assume, I probably should have put that in the problem here, assume the rate changes constantly. Okay, well, what kind of function do we know that has the rate changing constantly? I would say that this means that the change in the slope is constant. Change in slope is constant. And how do we represent the slope? Well, the slope is the change in the input divided by the change in the output. And if the change in the slope is constant, that means the function is quadratic. Okay, well, what can we build from this? Well, we know that the number of hours each week for a person who would be 13 years of age is 40 hours. And we know that initially that increase from, remember the initial rate of change from 0 to 40, that increase is roughly 2 hours. So I'm going to write 2 times an increase in age of 1 plus the 40 hours. So for a person that's 1, A equals 1, so in other words 14 years old, they watch or use the internet for about 42 hours a week. But it's not the same each year. So if I change the age of a person from 14 to 15, I'm not going to assume that I can just add 2 to that again and get 44 because the rate changes constantly. So the slope changes as the input increases. All right, well, that means that all I can write, since that is an unknown value, is that n equals A was probably a bad variable to pick. Let's pick a different variable here. Let's call this t for age. That's probably a little bit better. Okay, so this means that this is going to be of the form at squared plus 2t plus 40. All right, well, that is basically the best that I could do with this, where a represents half the change in the rate of change. So in order to complete this model, I need to know what the half the change in the rate of change is. Well, anytime I'm given more information about this, I can actually plug in values or an ordered pair for t and n, and I can solve for what a has to be. So you might say, oh, well, I can solve for that because I know that 0, 40 is on the graph. And if that's the case, then I know that n equals at squared, n equals at squared plus 2t plus 40, that what I do know is that I should be able to plug in 40 for n and 0 for t and be able to generate a lot of constants in this equation. But here's the problem. Guess what ends up happening? Well, a times 0 squared is 0, 2 times 0 is 0, so all I get left with is 40 equals 40. Well, that didn't help me solve for the constant. So I need another point. I can't use the vertical intercept because that just zeroes out the whole term that involves the variable I want to solve for, and that's not helpful. So it's not that it's wrong, it's just not helping us do what we wanted to do. Well, here's some more information. Suppose it is also known that a 40-year-old averages 21 hours per week. Well, what does that say? So someone who's 40, which means that that's 27 years beyond the age of a person who's 13, right? So A equals, we call it T. T equals 27 would mean that the person is 13 plus 27 equals 40 years old. And so it drops down to about 21. So what is this going to look like, assuming this is a quadratic function? Well, we have initially growth, but in the long run it appears that this is going to have to eventually drop off, which seems to make sense, right? The amount of internet usage, probably as you get older up until a certain point your usage increases, but maybe after that most people just typically don't use a lot of internet. Just, I don't know, that's possibly an argument we could make, and that probably would make sense. Probably better things to do than surf the web. Okay, so we know that this point here is, let's see, we said 27 comma 21. Why is it 27? Because this axis represents the number of years a person is beyond age 13. So a 40-year-old would be 27 years beyond age 13. And again, that was just a way of representing t equals 0. Let's let that symbolize a person who's 13 years old. Okay, and so now we have this point. We have 27, 21. And this will make solving a lot easier, because now I can say, okay, well, 21 is n, and the corresponding t would be 27. So I now have a times 27 squared plus 2 times 27 plus 40. And now I can solve for this. Well, how do I do that? This looks really hard to do. Okay, well, let's take it kind of step by step. Well, one way would be to put this side in your y equals and put this side in your y equals and see where they intersect. But we're going to see that this is actually a really pretty simple equation. Okay, so let's look at 27 squared. So 27 squared is 729. So really this is a times 729 plus, well, what's 2 times 27? 2 times 27 is 54. And then we have plus 40. So I can combine those, and that gives me 94. A times 279 is really just 729 times a. Make that look a little prettier. And 21 equals that. Well, what kind of function did this reduce down to? Well, this is now linear. And that happens whenever we plug in constant values, that we reduce it to a linear function. So now I just need to figure out what value of a multiplied by 729, I keep saying, yeah, in this case it is a, plus 94 gives me 21. Well, I can subtract 94, and yes, I can do this by solving, and that would be equally as right, but it's probably a little bit faster to not have to worry about adjusting our window. So 729a equals negative 73, divide by 729, divide by 729, and I get, let's see, 729, probably pretty small, ugly decimal. So a is about approximately negative 0.1. So that lets me complete my equation. N equals negative 0.1 t squared plus 2t plus 40. That's really, really cool. So how do I check that this actually works? Well, one way is to plug my point back in. If a person who is 40, I would plug in 27 for t, make sure I get 21 hours for an output, but also I want to check that my original point works. So a person who's 14 years old, well, a person who's 14 years old would have a t of 1, so 2 times 1 plus 40, and so what do we get? Well, we get negative 0.1 times 1 is negative 0.1, plus 42 is equal to about 39.9. Well, how much did a person who was 14, what did we learn about a person who was 14? Well, that person was on the internet for about 2 hours more than a person who was 13. Now, we were pretty close, but with rounding and everything else, we got 39.9 instead of 40, so because we rounded the value of a. So you can see this is a really tough problem because there's a lot of information here. I probably should have given you this piece. I would have done that. I need to be careful because that tells you what you can assume. And if the rate changes constantly, then we know for a fact that's a quadratic function.